video we are going to discuss about morphological image processing. So morphology, a branch of biology that deals with the form and structure of animals and plants. So morphological image processing is used to extract the image components for representation and description of regions, shape such as boundaries, skeletons and convex hull. So in the case of morphological operations, ones are considered as foreground and zeros as background. So basically morphological operations works on a binary images. So here one are considered as foreground and zero as a background. So the location at which one are present are considered as foreground. So here V consist, the location of this one is 1 comma 1, this one is 1 comma 3, then 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2 and 3 comma 3. Now the first in this one is a reflection. The reflection of a set V denoted by V hat is defined as V hat is equal to W for all W such that W is equal to minus times of V, for where small v is an element of capital V. Now the next definition is translation. So the translation of a set B by a point Z is equal to Z1 comma Z2 denoted by B of Z is defined by Bz is equal to for all C such that C is equal to B plus small z, where small b is an element of capital B. Now I am going to explain this one with the help of a simple example. For example, we consider the same V. This is an image where 1 is corresponding to a foreground and 0 is corresponding to a background. So V consists a location, spatial location where there is a 1. So V is this one. Now if we need if we want a reflection, then what we have to do? We have to W is equal to minus times of V. So every spatial location will become minus. So this 1 comma 3 becomes minus 1 comma minus 3. 1 comma 1 become minus 1 comma minus 1. 2 comma 2 will become minus 2 comma minus 2. Similarly 2 comma 3, 3 comma 3, 3 comma 2 and 3 comma 1 will become minus sign. All these spatial locations becomes minus. But one thing you have to remember that amplitude is not negative. Only its spatial location changes in the case of reflection, not its intensity value. Now with the help of this example, you can clearly understood what reflection means. So initially this one is an image where 1 is corresponding to a foreground while 0 is corresponding to a background. Now we are going to take the reflection of this one. So as we are going to take the reflection, its spatial location changes. So now initially there is a 1 at 1 comma 1. Now the 1 will be at minus 1 comma minus 1. Similarly, there is a 1 at 1 comma 3. Now it will become minus 1 comma minus 3. There is a 1. Similarly, for 2, there is a at 2 comma 2 there is a 1. So similarly at minus 2 comma minus 2 there is a 1. At 2 comma 3 in the original image there is a 1. So minus 2 comma minus 3 there is a 1. Similarly for 3 comma 1 there is a 1. So now minus 3 comma minus 1 there is will be a 1. Minus 3, 3 comma 2. So minus 3 comma minus 2. 3 comma 3. So minus 3 comma minus 3. So this V is corresponding to the original image and this one is corresponding to the reflection. So V hat represent reflection. Similarly for translation, initially, now for translation, we assume that translation is corresponding to Z, which consists 1 comma 1. This one is an original image, that is B So B is going to be translated by Z. So now BZ is what? BZ is B, the new element will be B plus Z. So initially the B is at 1 comma 1. So now it will become 1 will be add to 1 and another one will be add to 1. So now it will become 2 comma 2. Initially there will be a 1 at 1 comma 3. So now we add this one. 1 plus 1 is 2 and 3 plus 1 is 4. So it is corresponding to 2 comma 4. So in this way the whole elements are translated. Only those elements will be translated which consist 1 or foreground. So this one is an original B and this one corresponds to an original B and this one corresponds to a translated B. So now the new matrix will be, new image will be this one. Now the reflection and translation can be understood with the help of this example also. This one is an original image. Now it has been reflected one. So B hat is this one, where all the spatial location becomes negative. And now this one is a translated by Z1 and Z2. So this one is a translated image. Now, in morphological operations, structuring elements plays an important role. It is a small sets or sub-images used to probe an image under study for properties of interest. So these are the various examples of structuring element where this center element is an origin. So this one is a disc shape, this one is a square shape, this one is also a disc shape, this one is a vector shape. So these are different kind of structuring elements. This one is, as I already told you, that this one is center element is an origin. So this one is an original set A and this one is structuring element. And the C, this one C, the set padded with a background element to form a rectangular array provided a background border. Now this D represent structuring element as an rectangular array. So this accommodate the entire structuring element when it is origin is on the border of the original set A. For example, when this will be overlap at this position, so this origin will be at this position. Origin of B visits every element of A. At each location of the origin of B, if B is completely contained in A, then the location is a member of the new set. Otherwise, it is not a member of the new set. For example, if B is completely contained in A, if this position lies at this position, then this one is 1, 1, 1, 1, 1, 1. So if origin lies at this position, so this there is also 1, there is also 1, there is also 1 and there is also 1. So it will completely fit at this position. So this will be a member of new set. Otherwise not. So once, for example, when it coincides with this position, since these are not ones, so it will not be a member of, this pixel will not be a member of the newer one. So you can see that this pixel is not in this in the newer set. So if B or this ones are completely fit in this position, fit in this one, then it will be only the member of the newer one. Now, some basic properties of morphology are erosion. So erosion and dilation are the fundamental properties of morphological operations. So erosion is the set of all the points in an image where a structuring element fits into. Consider each foreground pixel in the input image. If the structuring element fits in it, write a 1 at the origin of the structuring element. It has a simple application of pattern matching. Input is a binary image and structuring element containing only ones. You have to remember it. that if the structuring element fits in, write a 1 at the origin of the structuring element. And the definition of erosion is this one. With x and b as the set in Z square. Z square is a two-dimensional space. For example, an image. The erosion of x by b denoted by this symbol is defined as for every element for every value of p is an element of Z square, means image space, such that p plus b is an element of x, where small b is an element of capital B, this structuring element, and x is an image, original image. Now I am going to explain with this example. For example, this one is an input image and this one is a structuring element. Now if structuring element coincides with this one, it does not completely fits this position. Here 1 1 1, here 1 0 and 0. So in the place of the structuring element center we have to put 0 because it does not completely fits. Now again does not completely fit, so again we have to write a 0 in the place of center element. Again it does not completely fits because here 0 0 and 1, here 1 1 and 1. So again we have to write 0 in place of structuring element, this one. So it's at the origin of the structuring element. Now again here, since there is a 0, here it is a 1. So again does not perfectly match or perfectly fits. So again 0. Now it completely fits. 1 1 1 and 1 1 1. So in the place of structuring element origin, we have to write 1. Again there is a mismatch, so 0. Again there is a mismatch, 0. Again there is a mismatch, 0. Now same thing can be explained with the help of this example. This one is an image that is denoted by A, whose width is, whose height is D, and this one is structuring element. If structuring element completely fits, then only there is a 1. So once it will be scanned throughout this one, once this origin will be placed here, so there will be a no 1 here. So it does not completely fit, so it will erode D by 4 width of pixels here, here and here. So you can see that this one is a dilated, eroded output image. Similarly, if we change the structuring element, the output structure will be changed. So this one is correspond to this one. If we are going to erode this A with this structuring element, then this one is an output. Now, if we applied an erosion technique on this image with a structuring element of 11 cross 11 pixels, that all the 11 cross 11 matrix has 1. So it will initially erode all these final lines. But as you can see in this figure that there are 2 lines remains because the width of this line is greater than 11 pixels. So that cannot be eroded. If we take a 15 cross 15 structuring 15 cross 15 pixels structuring element, then this line has been also eroded. If we increase the structuring element size, for example 45 cross 45, you can clearly see in this figure that these lines are also removed. So you have to only remember that structuring element has to be completely fit in the image. Then there is a 1 at the place of structuring element origin. Now the next one is a dilation. Dilation is set of all the points in the image where structuring element touches the foreground. Consider each pixel an input image. If the structuring element touches the foreground image, write 1 at the origin of the structuring element. Again, the input is a binary and the structuring element consists only ones. Now the definition is X is an image and B is a structuring element as a set in Z square. That is a two-dimensional space. The dilation of X by B is denoted by this symbol. And the definition is for all and the definition is P is an element of Z square such that P is equal to X plus B, where X is a small element of capital X and small b is an element of capital B. Now I am going to explain with this example. Initially, for example, I have this image where x is represented by this one, where there is an 1, and this one is a structuring element. So now what is the definition? That the new element will be a will be a summation of b plus small x. So initially b will be 1 at 0 0 and 0 1. So 0 0 will be added to all these elements, and similarly 0 1 will be added to all these one. So now the dilation is this one. 0 0 will be added to this one, then 1 comma 3 to 3 comma 1 will be repeated, and then again we have to add 0 comma 1 to all these pixel positions. Now there are some common points, so we have to remove this one, all the common points. So now this one, similarly, if we are taking the two-dimensional structuring element, then 1 at 0 comma 0, 0 comma 1, 1 comma 0, and 1 1. So we have to 0 comma 0 has to be added at this one, all these spatial locations. Now after that 0 comma 1, because there is a 1 also. So after that we have to add all 0 comma 1 to all these spatial location, then 1 comma 0 and 1 comma 1. So now x dilated b is this one. We have to remove the common elements, and then the output image is this one. The dilation can be understood with this simple example. As it touches its foreground, it touches the foreground, this structuring element. So we have to replace this one, the origin of the structuring element, positions with 1. Now once we move this one, now it does not touches the foreground, that consists 1. So there will be a 0. Again it touches this one. Structuring element center is this one, and it touches the foreground, 1 comma 1. So this position has to be replaced by 1. Again it touches, so 1. Again 1, 1, 1, 1 and 1. The same example can be explained with the help of dilation also. This one is the original image, and this one is a structuring element. Now you can see the size has been expanded by d by 8 on the left side and d by 8 on the right side. So, and similarly on the top and bottom also. If this structuring element is dilated with this one, then again we found that the width has been increased by d by 8, d by 8, and the height top and bottom has been increased by d by 2 and d by 2. So dilation elongate the images, while erosion shrink the images. Similarly, if we applied the dilation on this image, we can clearly see that these structures are not cleared. These letters are not cleared. So if we dilated this one with this structuring element, we can see the output in the output image that it is better as compared to this one. The quality of these letters also depends upon the structuring element. But you can clearly see that after dilating this one with this structuring element, the quality has been improved. We have studied this similar example with the enhancement of this one example with the help of low pass filter, but the advantage of morphological operation over low pass filtering is that morphological method resulted directly in a binary image, while low pass filter on the other hand started with a binary image and produced a grayscale image which could require to pass with a thresholding function to convert it back to a binary form. So another example of dilation is this one. So dilated fills, so it expands the foreground. So you can see now the size of this hole has been shrinked. The same example, if we erode, then we find out that the size of this hole has been increased. So it will erode. So erosion shrinks the images. So you can see that the foreground has been shrinked. While dilation increase the size. You can clearly see that the boundary of this one has been increased after the dilation. Now the other operations are opening and closing. Opening generally smoothens the contour of an object and breaks narrow isthmus and eliminates thin protrusions. Closing tends to smooth the sections of contours, but it generates fuse narrow breaks and long thin gulfs, eliminates small holes and fills the gaps in the contour. So now opening operation is defined as, first you have to erode and then you have to dilate. So now A is a image of set A is eroded by structuring element B, and after that it has been dilated by same structuring element B. Then it is called opening operation and it is denoted by A opening B. In the closing operation, this dot has been completely filled, in which first we have to dilate and then erode with the same structuring element. So opening similar to erosion, spot and noise removal less destructive. So in opening what we have to do? First erosion and next dilation with the same structuring element. Input is a binary image and a structuring element contains only ones. Now for opening, take the structuring element and slide it around inside each foreground region. All pixels which can be covered by the structuring element SE, with the SE being entirely within the foreground region, will be preserved. And all foreground pixels which cannot be reached by the structuring element without lapping over the edge of the foreground object will be eroded away. Opening is idempotent. It means repeated application has no further effects. If we apply twice opening operation, it has the same result of applying the opening once. Now, this one is an example of opening operation. So X is this one and B is this structuring element. Now first what we have to do? We have to erode. So now if we apply this one, then it will erode all the ones because does not fit with anyone. Completely fit at any position. So at the position of this structuring element, this center, this will become 0. Once it will be fit here, since there is a 0 here, so it will erode this one. Similarly for this one, this one, this one and this one. So X eroded B, the output is this one. Now we have to dilate it. Since there is a no one, the output will remain 0. But we have to dilate with the same structuring element. Now closing operation, that is similar to dilation. Removal of holes tends to enlarge the regions and shrink the background. So closing is defined as dilation followed by an erosion using the same structuring element for both operations. So first dilation and then erosion. Input is a binary image and a structuring element containing only ones. So in closing operation, take the structuring element and slide it around outside each foreground region. All background pixels which can be covered by the structuring element, with SE being entirely within the background region, will be preserved. All background pixels which cannot be reached by the structuring element without lapping over the edge of the foreground object will be turned into foreground. Closing is also idempotent. It means repeated application has no further effects. The output will remain same even if you apply twice, thrice number of times closing operations. So we consider the same example. This one is an X and this one is a structuring element. First what we have to do? First we have to dilate. So once match with this foreground, once it will be here at this position, it matches the foreground. So at the position of the 1, here we have to put 1. Now again, once the origin will be at this position. So this one is corresponding. Then there is a one at this position. Now, when this one moved out to be here, there is a foreground at this position at once. So we have to put it one here. Similarly, it has been expanded. So first we have to, what we have to do? First we have to dilate. So in place of thin line, now it becomes thick line. You can see that there for 3 pixels, there is a 1. Now we have to erode it. So now but after erosion, we can find out that here only 1. So there is a thin line only. And this one again becomes 0. So it expands the image as compared to opening operation. Now you can clearly see this one is a closing operation with 22 pixel disk. So first we have to dilate. So what dilation will do? It will expand and also remove these holes, these smaller holes. Since we have to taken 22 pixel disk, might be the size of this one is greater than 22 pixels, so it has not completely dilated. And after that we eroded, so only these pixels are eroded. So we completely remove these smaller pixels. Now closing operation, another example is this one. This one is a grayscale image, and when we are doing some kind of thresholding operation, you can see that there are these holes or dark pixels that are present in this object. While when we are performing a closing operation, we perform completely white, or there's a completely whiter pixels in this object. So it performs better than the thresholding operations. So this figure shows an image which have a lot of noise. This is a fingerprint and there is a lot of noise. For first, so what we do, we first operate erosion. So you can clearly see that all these noise has been removed. If we erode this image with this structuring element, then all the noise has been removed. So, but you can also find that the ridges has also been eroded. The background noise was completely eliminated in the erosion stage of the opening, because in the case all the noise components are smaller than this structuring element. The size of the noise element, that is dark spots contained within the fingerprint, actually increases the size. The reason is that these elements are inner boundaries that increases in the size as the object is eroded. And now an opening operation has been performed. First erosion and then there is a dilation. So this figure D, the net effect of opening was to eliminate virtually all the noise component in both the background and the fingerprints itself. However, the new gaps between the fingerprint images are created. As you can see here. To counter this undesirable effect, we perform a dilation on the opening. So this one is an opening operation. We again perform a dilation. So most of the bricks were restored, but the ridges were thick, a condition that can be remedied by erosion. So again we performed an erosion operation. So first we perform on opening operation, there is a dilation, and then this one is an erosion. So finally you can say that first opening and then closing operation. So in the final we are going to get an overall improved version of an image. Now this is another example of opening and closing operations. So figure A, this A shows a set capital A, and this figure shows a structuring element of disc-like structure. And when this disc-like structure, we have what we have do, we have eroded or erosion operation has been performed on this set of A with B. So when completed, this process resulted in a disjoint figure. When we performed a erosion operation, then finally we are going to get this output image that is shown in figure D. You can see that there is an elimination of the bridge between the two main sections. So this bridge has been eliminated as the size of this structuring element is greater than the width of this bridge. So this has been completely eroded. Not what we have to do, we perform a dilation operation on this one. So when we performed a dilation operation on this one with this structuring element, the image size has been enlarged. So this one is a finally an opening operation. Similarly, if we performed a closing operation on this image, in this image with the help of this structuring element, so it enlarges the images first. So this one is a dilation operation, and then we perform the erosion operation. Now you can see that the size of this structuring element is less than the size of this bridge. So there is no complete erosion. So this one is corresponding a closing operation. Now the next one is a hit and miss transform. Used to look for a particular patterns of foreground and background pixels. Very simple object recognition. All other morphological operation can be derived from it. Means all the other morphological operation can be derived from hit and miss transform. Input is a binary image and structuring element consists of zeros and ones. Example of hit and miss structuring element that it consists both ones and zeros. It is similar to pattern matching. If the foreground and background pixel in the structuring element exactly matches the foreground and background pixel in the image, then the pixel underneath the origin of the structuring element is set to the foreground color. So it is very useful technique for pattern matching. If B denotes a set composed of D and its background, the match of B in A denoted by A hit or miss transform with B is equal to A eroded with D intersection A complement eroded with W minus D, where B is equal to B1 comma B2. So B1 is corresponding to object or foreground and B2 is corresponding to background. So A hit or miss transform with B is equal to A erosion with B1 intersection A complement erosion with B2. So I can explain you that what is hit or miss with the help of this example. So this one is a structuring element. Now I am going to slide or scan this structuring element over this image. So now there is a no foreground behind this structuring element. So it completely misses. So it is miss. Now you can see when it is here structuring element, then there is a one element which is overlapped with foreground. One structuring element is overlapped with foreground. So it hit but not completely miss or fit. Now next one is this one. Again there are 3 pixels which overlap with these structuring elements. So this one is a hit. Now it perfectly matches. So all the structuring element matches with the foreground. So it is hit. Sorry, fit. Again it matches with the completely with the foreground, so fit. Now again it misses. There is no pixel that is behind of the foreground that is behind the structuring element, so it miss. So the objective of this example is to find the location of one of the shapes, say D. So this one is an image or set A, which is a union of C, D and E. W is a window and the local background of D with respect to W is W minus D. Now, this one is a complement of this image. Now, if we dilate this one with D, as you can see that the size of this D or structuring element is greater than E, so it will be completely egoted, while some small portion remains here in C and D. There is only a origin point. Now when we perform a erosion with this W minus D and A complement, we will get this image. And finally, in the case of hit or miss transform, we have to take an intersection of this one and this one. So you can clearly see that this origin will remain in the intersection of these two images. So we are able to find out the location of D with the help of hit or miss transform. Now there are some basic morphological algorithms. First one is a boundary extraction. So the boundary of a set A can be obtained by first eroding A by B and then performing the set difference between A and its erosion. So first we erode A with structuring element and then we subtract it from the set A. So that will give boundary. Because after erosion the boundary has been removed, it will erode, and once we are subtracting it from the original image, then the boundary will remains and the rest will be completely eroded. So this one is a very helpful in finding the boundary. Now A dilated with B, we comes out to be this one. So boundary has been eroded. Now if we are going to subtract it, then we are going to get this one. That is only a boundary. So this one is an image. So first we have to erode it with a structuring element, and then if we are going to subtract it from the original image, then we are going to get a boundary. Now next one is a thinning, used to remove selected foreground pixels from binary images. After edge detections, lines are often thicker than 1 pixel. So thinning can be used to thin those lines to 1 pixel width. So sometimes when we are detecting the edges, the width of the boundaries or lines are greater than 1 pixel. So if we need only 1 pixel line, then we can perform a thinning operation. So in thinning operation, what we have to do, we have to subtract hit or miss of I, comma k with original image I, where k be the kernel and I be an image. If foreground and background fit the structuring element exactly, then the pixel underneath the origin of structuring element is set to 0. Else not. Note that the value of the structuring element at the origin is 1 or do not care. So example, this one, this is a structuring element. So first we have to, what we have to do? First we have to perform a hit and miss transform, and then we have to subtract it with this one. And finally we are going to get a 1 pixel thin line. Now thickening, used to go selected regions of a foreground pixel. So thickening can be I plus hit or miss transform of I, comma k. And if the foreground and the background matches exactly the structuring element, then the set of pixel at the origin is to 1. Otherwise 0. Note that the value of the structuring element at the origin is 0 or don't care. So if we perform the hit or miss transform and then we add it with the original image, we can clearly see that these are thickened. Thank you.